So we got a pretty cool example here. We have two springs. They're in series. They're both unstretched when VA and VB are equal to 0. And then we're going to hit point A with the force A and point B with the force B. They're all downward, so this is an axial problem. And the question is, give me VA as a function of these forces, and give me VB as a function of these forces at equilibrium using virtual work. So once again, probably said this already 3 or 4 times in 2 or 3 weeks, very simple geometry, fairly sophisticated ideas though. There's a couple things that there's a lot of different ways of attacking this problem. None of them are necessary, but they might help you kind of getting the signs right. As I said before, the signs are the hardest part. We're going to use this equation here. What I did here is I looked at the work of the forces alone, and then I looked at the work of the springs alone, and I set the work of the forces equal to a positive value and the work of the springs equal to a negative value. And then I applied the red boxed equation here. So let's take so dV is, and let's look at the work of the forces here. So the FA, I think it's pretty straightforward, right? It's the force at A times the displacement at A. So that's a virtual movement, dVA. And for FB, it's not so bad either. FB times dVB. So, and that's it. Now, this is a little complicated here, so you might have to hit pause and replay a couple times. Let's look at the work of the spring when spring A stretches. When spring A stretches, we have VA, and the work of that spring is KA VA times dVA. So that is the work. This is the force, KAVA times dVA, and it's a minus sign because we're talking about the internals. That's the work of spring A when spring A stretches. Now let's look at the work of spring B when spring A stretches. So the work of spring B is when spring A stretches. So I'm going to have to say spring A is stretching, so I'm going to say VA minus VB. That will give me a stretch of spring A. So I have KB times that stretch, VA minus VB, that's how much spring A stretches, times the virtual displacement of VA. And now I'm going to do the work of spring B when spring B stretches. So what do you think that should look like? When spring B stretches, you might hit pause and try to answer this. It's VB minus VA. So I have KB times VB minus VA times that virtual displacement dVB. So we can just collect some terms here, just bringing everything out into one big expression. And I grouped all the VA terms together, and I grouped all the VB terms together. So again, you might hit pause just to make sure that you got all that down. We're going to set dV equal to 0, but this is kind of an ugly little problem here. Maybe I'll rotate the camera. And you'll see that the only way this is going to work is if the parenthetical terms are both independently 0. Then the left-hand side is equal to 0. Because dVA and dVB are not necessarily 0. Of course, one or the other could be 0. But the bracketed terms both independently disappearing makes this whole term 0. So the first bracketed term is here, so I have FA, and I just did a little bit of algebra to simplify this. Then I went to the second bracketed term, right here, the second bracketed term. FB is KBVB minus KBVA. And what I noticed is I could do a little substitution here, except I just have to make a minus sign, and then it's going to look like this. So I have minus FB is KB times VA minus VB, and I could pop that into here. So this term becomes FB. So I simplify this first, that first parenthetical term down, and I have VA is FA plus FB over KA. And I take the second term in here, and I pop in what I just found for VA into here, and I get a nice neat expression. VB is a function of the two forces and the two springs. VA is a function of the two forces and the one spring constant. So like I said, you might have to hit pause a few times to really digest that one.